Welcome, all of you. I'm going to talk about loudness today, and before I start that, I will start with a small presentation of myself. My name is Torben Poulsen, and I have been working at the Technical University in Denmark for many years. I have worked with all these topics: psychoacoustics, audiology, audiometry, acoustic communication, speech intelligibility, hearing protectors, noise and hearing loss, and noise annoyance. I'm member of a working group under the International Standardization Organization, the Technical Committee 43, which is acoustics, and the working group number 1, which is concerned with threshold of hearing. And the other working group that I'm member of is working group 17, which is under a subcommittee of this acoustics one, subcommittee which is called noise, and the working group number 17 is concerned with measuring methods for hearing protector attenuation. But now I'm going to talk about loudness. Loudness, definition and description, that will be one of the things that I'm starting with. Psychoacoustics and the loudness curve, that's another topic. Loudness models, dynamic aspects of loudness, and some small other topics. That's what I will talk about today. Loudness, definition and description. Definition of loudness. There's a lot of words here. Loudness describes the subjective perception of the strength, the volume of a sound. So how big a sound is perceived, how loud it is, that's loudness, that concept. In Danish it's called hørestyrke, and those of you that are Danes may say, I have never heard that word before, and that's probably correct. In German it's called Lautheit, and in French, Sony. And the unit of loudness is zone or zone, some people will say in Danish. The ISO definition, the definition in the International Standardization Organization, is this one. It's an awful long one. Loudness is the perceived magnitude of a sound as estimated by listeners having otological and normal hearing, no hearing loss, depending on the acoustic properties of the sound and its manner of presentation to the listener. Clear enough, isn't it? Even though it's a long one. And in order to understand that, there are also some notes. Loudness is expressed in zones, that's what I have just said. Loudness depends primarily upon the sound pressure level, I think, upon the sound pressure, although it also depends upon the frequency, the waveform, the bandwidth and duration of the sound. So you can understand that loudness can be influenced by many different things. Note number 1, note number 2, note number 3. One zone is the loudness of a sound whose loudness level is 40-phone. I'm not going to talk about loudness levels in this presentation, but in another presentation I will talk about loudness levels. And note number 4, and it's all from the ISO document. A sound that is twice as loud as another sound is characterized by double the number of zones. So that's the way this is. A lot of words, but how to understand all this. An example. If you have a sound, for example a pure tone, with a sound pressure level of 80 decibels, sound pressure levels, that means levels that you measure with a sound level meter. I'm not talking about audiograms or hearing levels, something like that. The 80 dB, such one is perceived to be more than double as loud as the same sound at 40 decibels sound pressure level. So 40 decibel sound pressure level and double up to 80 dB sound pressure level, that loud sound up here would be more than double as loud. You will perceive it as more than double as loud as the 40 dB sound pressure level. But a sound with a loudness of 8 zones would be double as loud as the sound as 4 zones. It's a little complicated, but you have to remember that loudness is a perceptual concept. It's something that takes place in your brain, so to speak. It's not a physical concept. It's not something that you measure physically with a sound level meter, for example. It's all loudness is something that takes place up in your head, in your brain. It's a perception. I would like to explain a little bit about psychophysics, because that's the background for all this. We have a model here. We have a listener, which we usually sometimes call a black box, and we put in a stimulus into that listener. It could be a sound, and we can measure the physical strength of that sound level, sound pressure level, for example. And then when we put that in and ask the listener, how loud do you think this is? You will get a response from the listener, and you express that in a perceived magnitude. That's a psychological thing. For example, loudness. You could ask about how loud is this, and that's the loudness. So that's a subjective magnitude. Up here we are using some objective measure, an objective measuring instrument. Here you have two old guys, two German scientists from some years ago, many years ago, Weber and Fechner. And those two made some very interesting investigations about, for example, loudness, but also the feeling of weight. If you put something in your hand, how heavy is this? And you could smell things, or you could taste some sugar and be asked how sweet is this sugar. They did a lot of such investigations, and they came up with, or after that, they came up with a law which is called Weber-Fechner's law, and it's a relation between the perceived magnitude and the stimulus, this one up here. So it's a relation between the perceived magnitude and the stimulus, the physical stimulus that you're putting into that listener or test subject. And that relation is through a logarithmic function. There's a logarithmic relationship between the stimulus, the objective stimulus, the size of the objective stimulus, and the perceived magnitude. There's a logarithmic there. That's Weber-Fechner's law. And this was actually the reason, the background for introducing the decibel values in acoustics, for example, that there is such a logarithmic relationship. But later on, an American, Stevens, worked on the same lines, and he came up with a slightly different relation. He came up with Stevens' law, and there the relation is like this. We have again the perceived magnitude, and we have the stimulus up here in physical numbers, but he found out that you need another logarithmic, not just that one that Weber-Fechner found, but you need another logarithmic relationship in order to get the right things out of all this. So if we take Stephen's law, it will go like this. It's a straight line, simply a straight line in such a drawing like this, where you have a logarithmic axis over here. It's 0.1, 1, 10, 100. So this is a logarithmic one. And down here we have, in this case, phone, but we could also say it's a sound pressure level, 1 kilohertz. Then we can talk about decibels, and you know that behind the decibel there's a logarithmic function. So this is a double logarithmic relationship, and the Stephen's law, as we saw before, is such a double logarithmic one, and that will become a straight line in such a drawing like this. This is the loudness curve, and this expresses how much the loudness will be if you expose a person with a certain level of sound. And as we saw previously, one zone is equal to the 40 phone, so here 40 and 1. So the curve has to be like that. Now let's try to see. If I come in with such a signal like this, 40, it will give me a loudness, perceived loudness of 1 zone. If I then go 10 dB up to 50, from 40 to 50, then I can see here that the loudness will be 2 zones. That means the double loudness, and that means that we perceive this sound as double as loud as it was before. So such a 10 dB increase corresponds to a double loudness. It's very different from what you would see if you are an electrical engineer, where you'll say, okay, 6 dB is a doubling of the voltage, for example, or 3 dB is a doubling of the energy, and so on. But in psychoacoustics, when you talk about loudness, then it's a 10 dB change that will give you double up. I can continue that, go 10 dB further up and 10 dB further up, and go to 4 and 8, for example. Double up all the time. This is the loudness curve. I'll try to show it in a slightly different way, but same idea. If we have for people a sound level that goes from 40 to 60, for example, then for a normal hearing person it will look like that, and we will have a perceived loudness. These are not zone values, but it's a perception part. You will see it goes from 40 to 60 when it goes from 40 to 60 over here. That's easy enough. But now if you have a hearing loss, a person with a hearing loss, a usual age-related hearing loss, that means a cochlear hearing loss, where for an older person, an elderly person with an impaired hearing, then the threshold will go up to this place here, the elevated threshold for that person, the threshold that you measure in an audiogram, and then the loudness function will go like this red curve here. That will be the loudness curve for a hearing impaired person. And now you can see that these change from 40 to 60 will result in a much bigger change, perceived change, in the head of a hearing impaired person. And that's curious, that just because you have a hearing loss, when you listen to such a change in level, then it will be perceived differently for a person with a hearing loss compared to a person with normal hearing. That's what we call recruitment. Small changes in level near the threshold will result in big changes in loudness. I used to explain this by saying you can think about a situation where an elderly people talks with a young person. For example, the grandma talking with her grandchild, and then the old person says, okay, you should raise your voice a little bit because my hearing is not what it has been previously. And then that nice young person raises his or her voice a little bit, and then the old say, oh, yo, don't shout at me, I'm not deaf. And that's a very nice illustration of this situation here, that just because you change the level, the input level to the old person by a few decibels, then they will perceive, that old person will perceive a greater change in the loudness than the normal hearing person will do. But if we come up to the high levels, then there's no such change in perceived loudness. Then they will perceive changes or loudness in the same way. And this is one of the, not problems perhaps, but one of the issues that you have to take into account when you're using a hearing aid. A hearing aid shall amplify the sound when the input is very low, so that sounds become audible. But if the sound is reasonably high or just in middle level or so, then the amplification in the hearing aid should be almost nothing. And a hearing aid takes care of this, of course. They monitor the input signal all the time and adjust the amplification according to the level of the input signal. So a hearing aid can easily take this into account. No doubt about that. Yeah, loudness models. Loudness models. This is a little complicated, and I'm not going into all the details of all this. But these loudness models is also used in, for example, hearing aid fitting, in order to find out how to adjust a hearing aid, how to fit a hearing aid so that it fits to the person that uses it. We go from the free field to the eardrum, that's into the ear, through the middle ear, and then into the inner ear. And in the inner ear, you will convert the spectrum into a excitation pattern. And you know that in the inner ear, you have the basilar membrane, and you have all the hair cells sitting along the basilar membrane. They are sitting there, and when the basilar membrane is moving, then the hair cells are activated and will make nerve impulses. Then there is a box here where you change that excitation pattern to some loudness number, and then you'll calculate a certain area afterwards. I'm not going into the details. I just try to explain the the principle of all this. Here we have an example of this. This is a frequency axis. It's not actually an axis in hertz, but it has something to do with the auditory filters that we have in our hearing. But let's call it frequency. And up here we have a broadband noise. That means that it covers all the different frequencies, the whole frequency range. And that broadband noise will have a total level of 64 dB sound pressure level. That's the example, at least. Down here we have another signal. It's a narrow band noise. It's a narrow band, just signal in a narrow frequency range, but they have the same level as this one up there, 64 dB sound pressure level. Those two signals are coming over here in a moment. So we have the broadband noise and we have the narrowband noise, and they will measure the same if you put up a sound level meter and measure the level of these things, then it will be 64 dB in both cases. Now, if we go a little bit further and look at the excitation, the activity of the hair cells along the basilar membrane, then you will have activity along the basilar membrane all over the place for this broadband noise. But for the narrowband noise, you will have something that looks like this. You will see that in a presentation about masking, that it looks like this. And then for the last column over here, you have to calculate this area here, and that area, according to the signal here with the activity here, you will have an area that looks like that, and you will be able to calculate that this is 20 zone. But for the other one down here, you have an area that calculates up to 5 zones only. So here you have 5 zones, and up there you have 20 zones. So the loudness of these two signals, the broadband signal and the narrowband signal, those two have the same level, sound pressure level, measured in the physical world, but up in your head, these two will sound very differently. Their loudness will be very different. This narrowband one will only have 5 zones, whereas this one will be 4 times as loud. So this is a very good example of the problems of doing sound pressure level measurements with a sound level meter, that those numbers that you are getting out of a sound level meter does not necessarily correspond to what you perceive in your brain. So that's one of the models. Another way of looking at this is to look at this hearing threshold here that I have talked about in another presentation, and a mask threshold here, and the area between the absolute threshold and the mask threshold will correspond to loudness. I'm not going into the details of all this, but just to give you an idea of that, you can see a picture, so to speak, of the loudness through this area there. Okay. Then something about dynamic aspects. Here we have a time going, and then we start a stimulus that runs like this, and it stops over there. So a stimulus that starts and stops after a while. There will be something called temporal integration of loudness here in the beginning. It will last around 200 milliseconds. And there will be something called forward masking here after the signal stops, that also covers around 200 milliseconds. So the perception of sound will go like that it will grow up, and then there will be some loudness, and when the signal stops, the loudness will go down again. Let's look about the start of all this. Here we have the sound that starts there and stops over here, and the loudness will grow up like this blue curve. After a while, the loudness will have its full magnitude. There will be a time constant, which is about 100 milliseconds. And for those of you that knows about time constants and such things, you'll know that it will take about 2, 3, perhaps 4 times the time constant before this curve has reached its final value. So the time constant is about 1/10 of a second. But I say be careful, because short sounds are perceived as weak sounds. Use hearing protection if you're going to listen to short sounds. And short sounds are, for example, such as shooting from a pistol or another weapon. Short sounds, fireworks, for example, shooting noise, nail guns, toys, many toys have some click, click, click sounds, spoon in a cup, also a very short one. And the loudness of these very short ones, the loudness will grow up and then the noise is away. So loud, short sounds does not seem to be very loud. They are perceived very weak, but the physical pressure is with the full amount. I have some time ago I measured on such things like this. Maybe you can see it. Do you know these? Do you? Yeah, some of you. You shouldn't. They are forbidden now. I'm not going to pull it, but it's some of those where you can pull it and there will be a little noise out of that. And it doesn't sound of very much. But I have measured on these, and the peak level, these are the measurements that I made some years ago. The peak level of such a little thing like this is up to about 150 decibel, or even a little more. The 150, that's the level at your ear when you pull it out there. Then the level will be around 150. But the duration is very, very short. There are 2 milliseconds there, and you can see, let's take that one down there. The duration is less than half a millisecond or so. It's a very, very short signal, and that means that it goes a little bit up here, and then the sound is away, and the loudness will go down again. So it doesn't sound as a signal of 150 decibels, just because it is so small, so short. If I took a cannon, big, or a rifle or a pistol, the peak level will be the same, because it's an explosion. It's an explosion that takes place, so the peak level is the same. But for a cannon, big cannon, it will be a very long duration, and then we will say, oh, this is much too loud. I cannot stand listening to that. So a warning about the short sounds. I can see you can also show this by threshold measurements. Here we have measured the threshold of small tone pulses of half a second or something like that. And if I decrease the duration of the tone pulse down to 5 milliseconds, then you can see that it's about 20 decibel more. I need 20 decibel more level just in order to be able to listen to this or to hear it. And if I go a little bit higher up in level above the threshold, you will see here that 5 milliseconds needs 17 dB higher level than the 640 milliseconds for equal loudness at this level. But the loudness, and now I have called it forward masking, but it's the same. I'm going to talk about loudness here. We have the sound, and then the sound stops. But the loudness, the perception of a sound does not disappear immediately. It will take some time before the loudness disappear. It will go something like that, of such a curve like that. You can measure this by means of a small pulse, small Gaussian pulse, as a function of the duration from the signal stops and until you have this pulse after the end of the sound stimulus. And it will look like that. This is the level of the threshold. And that means that even if the signal has stopped and disappeared, there will still be some perception of sound. It will take some time before it disappears. And all this, also the temporal integration, and also this, which is also called forward masking, that is very important for speech and speech intelligibility, because speech consists of sounds, different kind of sounds. Some of them stop, some of them will have there will be some intervals, some pauses in between. And in order to understand what people are saying, you need to be able to hear these different things, and the loudness and the masking has an influence on that. Other topics. Some people thought back in time that it was possible to use such a loudness measure for hearing aid fitting, for example. And here I've shown a lot of 7 independent investigations where people tried to listen to different sounds and rated them whether they were comfortable to listen to, loud, very loud, too loud, or soft, very soft, and not heard. And the problem there is that the mean scaling, the people that said this is comfortable, that level in the different investigations covers a range of 30 decibels. So these different investigations were not in agreement. They did not all agree of what is a comfortable level. This is one thing. Another thing is here for some 10 normal hearing test subjects, 2 frequencies, and again, what is comfortable. Those 10 people were did not agree, let me say it in that way, did not agree about what comfortable is. The scaling comfortable covers a range of about 40 decibels. So 40 decibels, that's really something. So that's the clinical use of loudness. And then finally, something about the loudness function again. This is the way it looks for normal hearing, a straight line there. But for hearing impaired, we saw that it became very steep here, close to the threshold of that hearing impaired person. But the loudness function, some people will claim that the loudness function does not continue down here directly, but more or less stops here. And that means that if a hearing impaired person can hear something, then it's not just a totally faint sound, then it actually has some loudness. So some people would say that for a hearing impairment, the loudness function is not very steep near threshold, but it's elevated to a non-zero value, which means that we are not talking about loudness recruitment, but softness imperception, that you are not able, with a hearing loss, you're not able to hear really, really soft sounds. When you listen to something that you are actually able to hear, it will have some loudness, not just a very faint thing. Also, this has some implications for hearing aid fitting, of course. Yes, you have heard something about loudness, the psychophysics of the loudness curve, something about a model, dynamic aspects, and other topics, and that's it. Thank you for listening.